Okay, now we're gonna have, just to close this event, we're gonna have Bob. Bob, he was working with me in Freeport LNG. We worked together for almost 2.5 years. Such an amazing engineer, and I would like just to emphasize he spent a lot of time on this. He was working during the weekends to make this happen. I called him, and sometimes he was there on the weekends and really late. He was online really late, trying to put something together for us. I would really like to say thank you to him because he helped me so much during my time in CVNI, and I think it's key to know that based on us sharing the information, sharing our knowledge, you can build very strong relationships. Just like the relationship that I have with him is really strong, and I really appreciate all the information that he shared with me and all that he taught me. So I know that if we continue working like this, we're gonna make a really strong association where we can have like really good, not only co-workers but friends, because at the end of the day, this is not just work. It's something that we really have to enjoy, just like Bob enjoys. He has passion for piping stress, and I think it's the same for most of you guys here, if not maybe for everybody here. So just welcome, Bob, and thank you so much for putting this together for us.
As one said, I'm Bob Zimmerman. I'm the Vice President of the Piping Stress International Association, and I had the honor of being the first technical speaker for this. Some people say I picked a short straw, but I'm here to try to share the information. And in order to get through the presentation, which it isn't a real long one, why don't we hold the questions till the end? So if you have some questions, why don't we save them for the end, then we can discuss it so we don't get into a big discussions during the presentation, so we can get all the information presented, and then we'll take questions at the end. So the presentation here is called PSV reaction forces in a closed system. There's closed systems and open systems in these PSV systems. Now let me just define a few terms for you in case you're not familiar. We have a PSV is called a pressure safety valve. Sometimes they're called PRVs, pressure relief valves. Sometimes PRD is just a pressure relief device. But typically everybody in the business here for pipe stress knows, you hear PSVs, you have, you know what the type of valve they are. So what we decided to do on this one was there's been a lot of questions about what to do in a closed system versus an open system. An open system is like you have a fire hose, you have a lot of pressure, you're holding the hose, there's definitely going to be forces there. In a closed system, it gets questionable what kind of forces are in the system. I listed a few references on the paper here that were put together, and basically the main things we have are the ASME D31-3. This is taken from a recent project, and we were using the 2012 31-3 code, but it doesn't really matter for these PSV analysis. It's pretty much the same for all the current codes. But the main reference we have here is the API standard 520, and it's part 2. That's where they talk about the installation and more of these forces that we're talking about. During this recent, it's an LNG project, and the system we're going to talk about it's from the high pressure compressor PSV system. Now this system had 5 PSVs. It was 4 with 1 spare. And these are all very high capacity valves. There was 4 compressors on the project, and this was the high pressure side. And due to questions that were raised up, we decided to look a little more in detail on this one. And just for your information, the size of the valve, it was a 6Q8, which means it was a 6x8 valve, but these are very high capacity valves. Now, in people that have been in the business, especially doing the chemical plant designs, most of the PSV systems we have are closed. Just very rarely we have the open systems. I came from power side, did power work for a while. We had a lot of open systems. They were steam, they were air. Those can vent to atmosphere, but in the chemical plants and LNG plants, all these chemical facilities, we do refineries, they all have to go into a flare system, collected, and then burned off into the atmosphere. Now, really for these hydrocarbon vapors and also for the any chemical, the only real tool we have is API 520. That's the only equation basically the everyday engineer can use. In B31.1, which is the power side, we're dealing with steam, they have an appendix 2 in there, and that they give you a very detailed procedure, but it's well set up for steam, these open systems. But now this API 520, this is about the only equation we have. Let's go to the next slide. So everybody should be familiar with this. Even I remember when I first came to Houston a long time ago, we had look in the PSV catalogs, and always this type of equation was in there, and this is the equation in the 520 part 2. Everybody's probably familiar with it, and there's different, we'll be talking just in English units tonight. So this is the main equation where you have it. It's basically based on momentum. There's a momentum term, and then there's a pressure term. And then there's just a breakdown of these equations. But if we go down a little further, this equation is for open systems. But what's happening is this is the only equation we have. So we're using this in closed systems, and I always question why can it be? And just for a little background, back in the 90s, when we had a closed system, it was agreed upon with many different companies. Some companies didn't. You have a closed system, there's no unbalanced forces in there. It's closed, this event happens very quickly. It's just like you're having flow in a pipe. It is unsteady flow, but you have forces in all these systems. When you have steady state flow in any kind of piping system, a water pipe or whatever, there's forces there, but they're all equal and opposite. For a time in any PSV system when it releases, there's going to be some unbalances, but obviously in an open system when it goes to atmosphere, there's nothing to counteract that. In a closed system, you typically go from elbow to elbow, so if you have a force on one elbow, very quickly you're going to have a force on the other elbow, and that was the logic. We said there's really no unbalances, and we'll show just in a second what it says in the code. And so we had agreements, and it was even written into a lot of the company standards. Closed systems don't consider any thrust forces. They're not really significant. Don't be concerned about it. But recently, that's not the case. We've gone totally to the other side. Everybody's, or I shouldn't say everybody, many companies are using this and putting this in closed systems. And as we can see, we'll see a little bit later, that in these high capacity systems, the numbers get very high. And it sort of never made sense to me. And so we'll go on and talk a little further about that. So again, that's for open systems. Now, if this is straight out of the API 520, so it tells you right in there, it says the magnitude of the reaction force will differ substantially depending on whether the system is open or closed. But they don't tell you what to do. They just tell you that. And then they go on to further and say, well, there's another section, 583, right there. It says, how do you determine these reaction forces in a closed system? You say, well, see, this is what we used to read before. We used to stop at this first paragraph. You say, usually in a closed system, usually these unsteady flow conditions do not transfer large forces and bending moments into the inlet system. It says that. And that's where we stopped reading before. But then the next paragraph says, well, closed systems, however, do not lend themselves to simplified analysis techniques. A lot of times we're doing a production stress. We don't have time to do these time history studies and all this. We just want an equation, get the force, design our supports, and move on. We don't have time to do these big research projects. And it says, a complex time history analysis of the piping system may be required to obtain the reaction forces and associated moments. So first they tell us, well, really, there's usually not any large forces in there, but then they say, well, you know, during the transient cases or what have you, it's complicated and you may have to do a special analysis for it. We'll go on a little further. So we said, on this particular project, we had a joint venture partner. We had a lot of new employees come into the company. We had new management. We had some old timers, some new people, and a lot of people coming in. And even with our own offices in Europe, for the longest time, they've always put these types of forces in a closed system. And here in the U.S., the same company, we didn't do it, and we didn't have any issues. A lot of these were with ethylene plants and things of that nature, where there's an awful lot of PSVs, and we didn't explicitly design for these forces. We tried to stabilize the systems. We would just mainly design them for the standard conditions, thermal, if there's wind and these types of events, but not explicitly for these forces. But we tried, you know, we knew it was a PSV system. We tried to add more restraints to stabilize it and not have it too loose. And we didn't have really any trouble that we knew about. You know, we had large valves, and these things just didn't break apart, and we've had releases. On a lot of ethylene plants during the startup, they have to dump the whole plant, and all of them go. And some of them are just small valves, regular valves, or some of them are very high capacity. We didn't have any trouble. I don't think we were lucky. It's just that the understanding was is there's really not too much of an unbalance there. But see, nowadays we just can't say, well, our history shows that I'm an experienced guy, do what I tell you. It doesn't really happen. You can't do that anymore. Now they say, show me. Oh boy, hey, hold on now. I'm just a stress engineer. I'm not a process guy. I can do some fancy things, but I can't do that. So now you have to get other people involved. So now, okay, times have changed, okay? But when we said, so in other words, you know, we had different opinions on the same project. So we said, but in all we had a brainstorm just to see what we were going to do. And so the keywords that will keep coming up is right here. It says, the keywords for this were, are there any unbalanced forces? There's forces in there. Every system, there's piping forces in there. You have, like I said, any line that's circulating, any fluid. You have pressure forces in there, you just can't see them. They're pushing on each elbow. They're equal and opposite. They're trying to stretch the pipe. It's steel pipe, you can't see the stretch. There's also momentum going around each elbow, but the same momentum is on this elbow, on that elbow. The forces are there, but they're the same, so they cancel out. So the key is there any unbalanced forces? Let's see if there are. Then there's also, do we have more applicable data? That's been a buzzword recently. If you've seen a lot of the webinars from Caesar 2, from Hexagon, and also mainly from Pollen Research. With the new B31J, they've been talking about that for a long time. That's saying for SIFs on branch connections and stuff, it's been going on for 20 years. It's finally implemented. But the codes always say, use this simplified data unless you can find more applicable data. So if you can sharpen your pencil and show it, use it. The code is just a guideline to give you good practices. If you can do it more sophisticated, more accurate, you can use it, but like I said, you have to show, okay? So, of course, we had a lot of parties involved, and so all these procedures started coming. Here's the procedure that we use. Here's the procedure this is the way it has to be. The project is progressing. So we used these. We had no choice. We had to use these formulas. So we're coming out with, then all of a sudden, hey, wait a minute, this is not an ethylene plant. This is a LNG plant, 3 trains, very large facilities, all the ones that are being done, not just by our company, but many companies in the business. These are very large plants, and there's very high flow rates when on these compressors. And so we can't say, well, we did an ethylene plant, this is what we used to do before. They're sort of not the same. These are very high things, so we said, well, we got to be safe. Let's just go with what everybody's happy with. We'll design for these forces and do it. A lot of the stuff was already in progress. Civil already had the preliminary loads, and then we kind of started questioning these things. So we said, okay, we'll continue with that. And then, like I said, even if we could reduce these forces, it was starting to get a little bit late. But we said, well, we need to find out, because at the time we had a whole bunch of these plans lined up. It's a little different now. But there's some future work where maybe next time we can save projects. So we had some data here. So you've probably seen these type of sketches. A lot of times the companies copy them from one to another. They're talking about, okay, at the steady state condition, you have to put the forces, and I think everybody can see this. You got to put some unbalanced forces that are over when it goes from the PSV into a collection header. And the logic is that you're going to have some forces down into the header because you have a smaller pipe going into a larger volume. You go into a big, large volume, there's nobody trying to counteract that, but it has to be really big. You're going into, say you have like a 10-inch pipe going into a 10-foot diameter drum, maybe that's the case. But for some of these things, the sizes are not that big difference. And so we said, we don't really agree with this. You're trying to push this on us. We don't agree that there's a pressure force, an unbalanced pressure force in this closed system. We said, no, we're not going to do that. We also said there's an unbalanced momentum here. There's still forces there. You go into the header, you're still going to have these same forces. So we said we disagree with that. And even if we put these forces in, the way you put them in is you put them in axial. All you're trying to do is to stretch the pipe. The pipe can be stretched a lot without having any stress problems. So we said, if we go through all the trouble of putting these in and changing all the load cases, it's really not going to give us any stresses. What it's going to try to do is say, this is going to try to lift up this big giant header from these forces, and we say most forces are not there. So we say, no, we're not going to do it. But now we go to the next case is called the transient case. So this is, you said, well, we can't show that the forces are small, so we're just going to go with the traditional way that a lot of people are doing it now. We're going to use the API 520 equations, and we're going to put the force at the valve in the opposite direction of the flow. So that's what we did. So we agreed to that, and we said, but still, we're going with that direction, but let's see if we can find anything better. Okay? So the next slide is showing this is the system in hand, and again, so this is part of actually the compressor system, and it goes to air coolers. It's a very large model. And you can see the PSV is sort of down the end of this. This is actually an end of a header, and then we have this PSV system. So to put that all in the other calc is really not an efficient way to do it. It's isolated. So this is what the system looks like. We have the 5 valves that are here, the PSVs. There's an A and B, and then C, D, and E, and this last one is the spare. And so they go from an inlet header, go through these valves, and then collect into this big 56-inch flare. So let me just give you some geometry, if I can remember off the top of my head. We had the 6x8 valve that's there, and then from an 8, it starts to get larger. So we have a small section that goes to 14-inch, then basically it was an 18-inch, so they could save some money on the valve, and then they changed to 24-inch to go into a 42-inch collection header. And when we talked with Process about that, we said, well, these forces are large. We were calculating close to 20,000 pounds each, horizontal forces. And you got 5 of them, so we're going to say, okay, we're going to give Civil 100,000 pounds up here on the top of this structure. We'll show you some pictures later where it was, and we just don't have this system. We got 3 other ones that are similar. They're not high pressure like this, but the flow rates were the same, and basically the forces are proportional to the flow rate, so it doesn't matter the pressure. So we said, well, then we just talked to Process, and it's a very simple thing. Just walk over, talk to these people. We know these things are staged. The way this has worked is that just so you know that the inlet pressure was 1100 psi. That's 1100 psi. So it's a high pressure system. It was a class 600 valve. So they said we have A and B that are set at the set pressure of 1100 pounds. Then they can stage it. You know, they have their ways of sizing things. And so the C valve was set at 1125 pounds. And then the D valve was set at 1155 pounds. So they gradually step in and they size them accordingly so they can pass the flow to reduce the pressure. And then the E one is set at the just like the other ones at 1100 psi, and that's closed. They car seal close it. They call the valves are physically closed on that. So that's what it looks like. If we go down to the next portion, there's a blow up of it, and looks like the circle's got a little shifted, but right in here, this is where we applied the forces for the first load case for these. And I'm trying to show the loads there that we used about 18,850 pounds there. So say about 19,000 pounds was what we decided to use there. So when we ran this one case, we had the two 19,000 pound forces on there. And we treated it like an occasional load. I didn't want to get into all the load cases and things at this time, but it's an occasional load where we're going to put those on the system. And originally we said, well, usually what we've been doing, and a lot of companies have been doing, we got the force at the valve, so we're going to put the line stop right up on the outlet. And originally we started doing that because there's a structure here, they could get over there, put it right in the middle, right in line with this guy. But then these forces are big, and the civils say, hey, what are we supposed to do? And when they actually built a frame up there, but then after you framed it all in and you put a line stop there and all the design, couldn't get to any of these valves, so we said that's not a good idea. So we decided, you can see here if we go down to the next slide, it's just isolating one of the things, one of the systems from season 2. You can maybe zoom out a little bit. Okay, that's good. And so we put the force up here at the valve, and then this guy, that's one of those large rotation rod options in Caesar. So it's a rigid strut, so we decided, it's a very efficient design. We decided to put a strut around the elbow and put it here, and then we went right to the column line, a very clean design. And these struts can take a lot of load, even in compression, which this is going to be in compression. So that's how we modeled it. And you can see you have a little trunnion on the inlet side with a little guide on it. You have a big old trunnion here because this was stainless steel. Pipe, which was fairly thin, and then on top of that we got a whole bunch of new things that came out. We got FIV, flow-induced vibration, because there's a lot of turbulent flow, so now these specialist groups say, you got to design this thing for FIV. They say, well, by the way, there's another thing, it's called AIV, acoustically induced vibration. Now we're sort of making jokes about it, but these things can actually happen where the acoustic induced vibration is where the pipe vibrates circumferentially because there's just so much flow in there, it can vibrate, and then very quickly things can start to crack. So that was an AIV line. So the criteria now, and even in the past, is when you have branch connections, you have to use sweepolets, nice smooth connections, and also if you use a trunnion, it has to be a full encirclement. So there's a lot to these types of things, and so we said we don't want to put any more kind of welded attachments because they're very involved and whatever. We're just going to use a clamp and a strut, and that's what we did. Now the next picture will just show what the physical model looks in PDS. So, and it's the same view that we have there, and you can see these struts, we squeeze them in, but there's those struts, and here's it's right on a column line, so it was fairly easy for civil just to put a beam up there. And even there's some around the corner, we lined it up the same elevation, and there was another system right around the corner doing the same type of thing. And then there's other things too that is a different situation. There's HV valves, and then there's also blow down valves that they can use, just manually dump the system versus a safety issue with these. So that's what it looks like. We still haven't got to the forces yet. So let's go down. So now, in this job, this is the first time I realized what they were. Maybe they were on some other projects I used, but they said in this LNG service, they've had good success with what they call modulating PSV. So this is what one looks like. There's no spring there. So usually in a PSV, you have a spring, and that spring force counteracts the pressure times area that's in the inlet pipe, and then when the pressure times area on the bottom of the pipe exceeds the spring load, the valve will open. This is a little different. And it's actually a very nice design. They have these pressurized lines that go onto different areas. And so when it's under pressure, this line comes around, and actually the pressure from the line seals the valve. And it's the same type of thing they do with some count. It's just a balancing type of thing with pressures and areas and things. So that's right out of the API 520. That's a modulating pilot operated PSV. And so it's actually a much smoother thing. It just, when it operates, it just moves what it needs to release. It just doesn't pop open like the other ones. So it's a little different type of valve. And we go down, there's some more pictures of the valve, and so this shows you, obviously you won't be able to see it here, but it's just showing the three conditions when it's fully closed, starting to open, and then fully open, and there's different colors for the pressures and what's going on with the thing. And that's straight out of these catalogs. It was from Anderson Greenwood, which is now owned by Pentair. And during the discussions, we had the people come in because we were asking them about, is there any test data for these things in a closed system? They said they were looking at us with a blank stare. What are you talking about? We said, well, maybe, they must have done some kind of test on these to see, when they did the test, did they really have to restrain these things or whatever? And they said they've only done tests usually on small valves, which makes sense, because on these big valves, they can't generate enough flow rate that would simulate what happens in a real plant, because they just have an air tank or whatever, or maybe sometimes steam, and they usually do it on an open system also. So they really couldn't help us on the testing side to say what they've seen happen from their own valves. Okay, so that's what the valves look like, and now we can go down to the force calculations. So this is just a typical spreadsheet. And so now typically on the data sheets, you have a couple conditions. You have what they call a calculated maximum condition, which is based on the orifice size that's chosen, which is always bigger than the calculated size. And we typically use that one because when it's fully open, if you have the flow, that's the flow rate you'll get. As long as the machine or the system can provide that flow, you're going to get it. So we have to use that flow rate in the equation that we showed earlier. So, these spreadsheets are pretty common. So we said, okay, let's calculate the maximum. You can see right there, I'll read it for you. It's the momentum force is 19,610 pounds, so right around 20 kips. But then there's also that pressure term. We left it in there, but we said, we don't believe there's an unbalanced pressure in the system, but let's calculate it anyway. We don't have to use it. That was about 5.5 kips. So you can see, if we're just going to go blind in there, we're going to use the 25 kips. You can see previously we didn't use that. We used 18 or 19 kips. So that was that number. If we go down to the next slide, it's just showing the spreadsheet for the next one where you're putting the flow rate. So the flow rate on the previous one was almost 1 million pounds an hour, and then now the required was 730,000 pounds an hour. So those are big numbers. That's just for one valve. Okay? And that one came out to be about 15,000 pounds, and again the same pressure force. And if we go down, then there's a little summary down here that shows what happened here. So if we just do the calculations, we calculated, like, say, 19,600 pounds for the maximum flow. And, well, it looks like I forgot to change the title there, but this is now the required flow with the calculation yielded about 14,800 pounds. But then also, on all the vendor data sheets, they calculate this for us. So we said, what are we doing? They calculated it for us already. So on the latest data sheet, because when we did the study, that's why it took me a little bit longer to do it, it's been 18 months. I said, I always wanted to get back to that thing, take a look at it. When I opened it on there, I don't remember anything. So I said, okay. And then when I called our specialist who generated the stuff to give us this to give us the fancy data, they didn't remember what the spreadsheet was. They said, well, come on over. When I open it up, you'll see when I opened it, they saw these curves, and they said, yeah, oh yeah, I remember that. Let's talk about it. So that's what we did, and then I continued on with this report. But you can see here from the vendor data sheet, the current one, I went and pulled the current ones, which of course are a little different than the ones we did during the design. we'll say about 18,000 pounds, but previously it was this 18,850 number. So it went down a little bit with the final thing. But I'm just giving you the answer now. The process does a dynamic simulation, not for this. They do it for things that they need to do. They're process people. They have compressors they have to be concerned about. They do everything, you know, statically, but then they also have fancy options to do this dynamic simulation. In talking with the LNG experts, they say they do it for every plant. Sometimes they only do it for portions of it, but this one and for the future ones, they do pretty much the whole plant is in this model. They have air coolers, they have the compressors, they have the main cryo heat exchanger, have everything in there, and then they can do all these scenarios, and it helps them confirm what they did with traditional methods, and also many other things. That there's just so many things that they do for it. But one of the things is for all these PSVs, they have flow rate data versus time. They have velocity data versus time. They have pressure. They have all this time history data. And so we used that data and we calculated a load of 2,055 pounds. So basically we're talking 20,000 pounds using this traditional method, and I'm coming up with 2,000. So I sort of convinced myself, and this was during the project, it looks like I can just divide this thing by 10, and that's what we'll design for. But they said, wait a minute, Bob, wait, this is just one case. And wait a minute, you know, Civil's already got these foundations designed, the steel's all heavy. There's no benefit to doing that. I said, yeah, you're right. And this is only one case, which is not prudent to do that. If we did all 4 of these PSV systems and then, you know, looked at it with a little more time than I just did recently, then we can maybe make a trend, and that's what may happen later on. But you know, we're pretty confident. I even talked with these experts who generated all this sophisticated data. They said that's about right, and we're talking about pressures and things. Yeah, and so we're seeing that kind of number, which I still think is probably a little bit high. And then that sort of justifies to me. I'm not telling you to do it. I'm just telling you this is what trends we're seeing. That we had these systems in place, and really for a closed system, it really looks like there's not too much of an imbalance in the system. There's forces there, but they're not unbalanced. So now what I did is they gave so much data. Like when you open up the spreadsheet, which I'll just show you at the end. This is almost finished here, but I just put the curves in here because there's just so much data that they gave. And so this is really what the force was calculated. Now, I didn't do anything special for the force calculation. I used the API 520 equations, but I just did it on a time step basis. For each time, they had the flow rate, they had the other data that was needed there, and I used the temperature and everything from the data sheets and stuff, and I just calculated, but based for each time step. So we plotted the force over time, and this is when the valve opens, and there's reasons why we stopped at the 60 seconds. I'll show you later that basically when they did the simulation, there was they let it run for 60 seconds, and in this event, the peaks happened at about 2 minutes after it was open at the 3-minute mark. But then when we started plotting the curves, things started to not change too much after 60 seconds. And so we said, let's just limit the data that we're going to use to the first 60 seconds of the event. And so we can see from here, here's the force. The force is increasing at the valve as time goes on, but the change in force is not. And we're seeing that the change in force, and then I'm going to go way back to first principles. If we go back to first principles, is the force is proportional to the change in momentum. Momentum is mass times velocity. We have mass flow rates, we have velocities. It's the change. And this is Newton's second law. It says the force on a particle is proportional to the change in momentum of that particle. It's the change. Okay, so this is just pretty basic stuff. So that's what we did. And you can see that that's where that 2,000 pounds came from, and then it decreases from there over time. So that's what happened. And now we can show you some of the other curves that are there. It's hard to show them on these screens because we had 11 by 17 sheets and stuff like that. But here's the if you could just shrink it just a little bit, and then we can come down. We'll just show you the mass flows and things like that. So here's the mass flow rate through the valves. You can see as it goes up, the rate of the calculated or the required load that they said that they needed, just based on their standard calculation, was about 730,000, I think I remember, pounds per hour. But this never even got there. It got close, and so this is, the flow is increasing, but the change in flow, it sort of stops at about 100,000 and then goes down. So we're always talking about the change. So just to give you a feel for what it is, then we said there's the flow rate, here's the velocity curves, and sometimes they can get a lot faster than this as it starts and it was going up to about 350 feet per second, which is still pretty fast, but sometimes they get closer to sonic speed, which would be 500 to 600 feet per second. But you can see the change in velocity on time steps, was only like around 50 feet per second. So these aren't bad at all. These are big numbers, these are small numbers, the change from one interval to another. And obviously, the data they used every half a second for their simulation. We chose every 5 seconds because the curves were smooth. The larger time step you take, actually, you're going to get a little bit bigger number, but you're going to get the same peaks and stuff. So we're always talking about the change. So this was the velocity, what was found in there. The next curve is the momentum, the mass times the velocity. So you can see it's still increasing, but the change sort of peaks at that same time after about 5 seconds only, and then it just starts to decrease from there. And then this last curve is just showing, this is in PSIA now. So this is showing the 4 PSVs. Now you can only see 3 curves because the A and the B, the red one is the A, blue one is the B. They're happening at the same time. But you can see, like I was telling you, this is in the real scale. So like I said, they let the program run for a minute, then now everything starts to happen. So you can see we go over here, and then the peak happened at about that 182nd, which is the 3-minute mark, minus where you started, the 1-minute mark. It's about a 2-minute thing to get to the peaks. And then, like I said, you can sort of see when the next valve opens. It's not immediate, there's some time in here, and then the final valve opens, like that. So, but look at the scale here. We started at 35 PSIA, but the peak only went to 42 PSIA. So that's only about 7 PSI. But we said, on the data sheet, said the built-up pressure is 50. So that's your PA. No, there's no PA. This is 5 pounds over a long period of time. There's no pressure. But and I talked with one of the LNG experts. Oh yeah, when these things go, there's so much volume, you're not going to get any pressure in there. He said, you didn't need to see this. So it's sort of understood. So people, like I said, they're still, sometimes some companies are saying use API 520 just a momentum in closed system. Other than, oh no, you got to do momentum plus the pressure. The pressure is definitely out. Momentum, well, we might need a little more work, but we could see that it seems like the change of momentum still is not that significant. And then what they did, the last slide is just the process simulation is done using Unisim, and this is one of the examples. It can do many things. And he says it can be used for emergency depressurizing of flare systems. And actually for the ethylene plants, they're only doing basically the flare system to help confirm resizing the flare system. They're not doing the whole plant like they did on the LNG. And then you can also use it for compressor and surge control, which is very critical on these machines in the LNG plants. Could you open up the Excel file real quick just so we can see? So that's basically it. So basically the conclusion that I came up with is saying, well, we can design for these forces. It's obviously conservative, but it makes people feel good that we have these systems designed for these large numbers, just in case maybe I'm wrong. But I think from experience and all this type of calculation is sort of showing it's leaning more towards the zero force versus the full force. That's what we're seeing now. This is the data they gave. If we can go down, it's basically we just did some data here. Say on 11 by 17, the data's on the top. But if we could just go over and just hit some of these tabs to see when they gave this to me. You could just hit one tab at a time. So this is the numbers they're giving me. say, oh, this is going to help a lot. You know, just keep going across the tabs, just one tab after another. So look at all these numbers, because this isn't just this PSV. They got all the PSVs, you know, it's going on forever. And then they have their little things, and then they have these curves and so. But luckily, like I said, over in the sheet 28, one of the guys from the office of chief engineer, he went in and he copied the stuff just for this PSV system into the sheet 28 and put a couple curves in there, and then I took it from there. But you can see if they just throw this at you, and there you go. Like I said, so they helped us out. We worked as a team, and we came up with these. So that's about all I had for tonight. And like I said, this gave me an opportunity to give this presentation. And we want to do more of this where anybody can volunteer for this. Because originally, these get-togethers were supposed to be about modeling Caesar 2, giving technical stuff, and they ended up being vendor presentations or just social gatherings. So the intent of the PSI Association is anybody can do it. If you want to volunteer, you have a subject, it's something as simple as modeling a trunnion, because I've never modeled trunnion Caesar 2 with the offset method. Maybe that's the best one, but I've just never done it. If somebody wants to do that, say here's what we did with the offset method versus another method, and compare that. That's all you need to do. It could take 15 minutes or whatever, and that would be adequate for a presentation. We can do a few of those different people. So that's the intent of this. So like I said, we've had this study for a long time. We couldn't implement it because we were too far along. But obviously, just as being good engineers, we're not going to take one case and say, do it everywhere. We got to look at some more in the future. Of course, if the company wants to do it, and then, because they're going to have this data on other plants, and a lot of other companies are going to have it, the same thing. This data's there. They're not doing it for us. They're doing it for themselves, but we get it for free because the data's there, and we can use it for these types of study. So that's all I had for tonight. Thank you. Yes. I'm sorry. And then any questions now? We can bring it open to questions. Yes.
Yeah. First of all, the concept of anchoring at the closed system. Correct me if I'm wrong, but did some of that emanate from our European friends, the Energy
Yes.
Institute?
Yeah, I think it mainly came from Europe because it seemed to be standard practice. We had even on a previous large project, we had some people from the Egypt office come over, which is now closed, but they worked with the Europeans, and they started. We were doing this, and we already had it even in our procedures. Don't do these forces, and they were starting to put them in and do all the calculations, and we had to sort of calm them down because this is how we've been doing it. So yeah, I think it's mostly from Europe, and then of course for Asia, a lot of times they're working with a lot of different U.S. companies or European companies, and then they integrate those procedures into their own. So if they're doing it, then they're going to do it, but maybe they don't know why. It's just good things. This is a Western company doing these types of things. We'll do the same. But I think it wasn't here because I think a lot of companies didn't do it, and now. I shouldn't say just recently, it's been a trend that more and more are doing it because we really don't have any other way to do it.
Yes. And one second point that needs to be mentioned on these valves, it's critical in terms of on the outlet side where you have reducers, it's important to follow those so-called rule of thumbs or guidelines of having so many pipe diameters away from, as you transition up. You and I were in that meeting with that valve vendor, and he had various control stations up there with different configurations, and he could literally, just looking at those configurations, determine which ones looked like were going to be problems. And then a lot had to do with the expansion of those pipe diameters as you left the valve and how many pipe diameters. The takeaway that I got from that was that is the most important thing that you have to follow, because if you don't, you're going to run into real problems.
And I think you're right, and I think these were for some anti-surge or for these hot gas bypass valves, or in general we've had discussions and actually implemented for these wet down valves, because when you have these big pressure changes, wet down valve PSVs, let's get some straight run in there, but treat it sort of like a meter run. Go 10 diameters, something like that. And the process can help with some feedback too. But you can see, traditionally on the PSVs, they're always sort of like this. They come out and you just go down and go your merry way. Although on, like I said, these ethylene plants, we usually have two types of headers. We have a cold and a hot flare. So some in the PSVs are coming from both sides of the rack. They're just lined with them. And sometimes you're going to the far one, and sometimes to the one closer. You're not really going down. You're just going over and in, and then trying to work out the flexibilities and those kind of things, checking those types of things. But yeah, obviously, if you could develop the flow a little more, it's going to calm everything down even further, which is good practice. But nowadays, it's a little bit hard sell. But on these letdown valves and stuff, it's sort of getting into the practice now where you have to have these diameters. For a while there, the pumps all used to be very tight. And now they're saying, nope, you got to have your 5 diameters in front of the pump. And now everybody does it. And I think on these other things, you just got to start implementing it. And it is a good practice. It'll alleviate a lot of problems. You don't have to do any calculations. You just know it's going to be calmed down. There's not going to be much vibration.
And it's probably important too that during startup, if you have the opportunity to be out there, it would be good to look at these kind of systems, because if you're in the control room, you can talk to the operators and say, give me 20 minutes, I'll be down across from this area. You know, create a situation where a couple of these valves can relieve. You can be there looking at it as it takes place. That type of information is invaluable when you come back to the office, because then you can say, hey, I was out there during an unbalanced situation at a startup condition, nothing happened, yet we erected this monument up there with all the steel. You know, you could have saved the company a lot of money. So it's important to be out there if you can convince the right people to be out there during startup, and not just simply the process people. Because it's definitely a learning experience.
Yes. Is there any other questions? All right, thank you.
Okay, well.
All right.
Once again, just to close this tonight, I want to say thank you everybody for coming. It was a little bit long presentation, but please let me know if you have any comments. You have my business card. You can send me an email whenever you want. I'm pretty quick to reply your emails. If you have ideas, if you have any vendors, if you want to volunteer to have a presentation for us, feel free to reach me in my email address or in my phone. And at the end of the day, we're just gonna need a lot more volunteering from some of you. So also, if you want to help setting up this as a non-profit organization, it's gonna take me a while to do it by myself and with the officers that I have. But if I can get some ideas, maybe another suggestion about another restaurant or anything that you think it would be good for the association, let me know, and we'll try to make it happen. So once again, this is, and I think that's my favorite statement. This is to preserve it's the legacy for piping and stress engineering. That's what the PSI Association is about, and I just want you guys to say again, thank you very much for coming, and hopefully we're gonna have another event on December the 7th if I'm able to get another sponsor, okay? So that's the plan. Let me know if you have any comments, any ideas, and thank you very much for coming, okay?
I never see the technical side, so I always see the sales side.